I want to start with a number. The number is 10 billion. 10 billion. 10 billion light years. That is the approximate length of a structure that astronomers have identified in the large-scale distribution of galaxies in the observable universe. A structure so large that if you tried to cross it at the speed of light, which is the fastest speed that anything in the universe can travel, the journey would take 10 billion years. For context, the entire observable universe is only 93 billion light years across. This structure spans more than 1/10 of the entire observable universe. It is not a galaxy. It is not a galaxy cluster. It is not even a supercluster of galaxy clusters. It is an arrangement of galaxies, quasars, and galaxy clusters that extends across a volume of space so vast that the standard model of cosmology, the framework that has successfully described the structure of the universe for 30 years, says it should not exist. It is called the Hercules-Corona Borealis Great Wall. And I want to be precise about what I mean when I say it should not exist, because that phrase is often used loosely in popular science, and I want to use it with the precision it deserves here. The standard cosmological model, Lambda-CDM, makes a specific quantitative prediction about the maximum scale at which structures in the universe can exist. That prediction follows from the physics of inflation, from the initial conditions of the Big Bang, from the way gravity amplifies tiny quantum fluctuations into the large-scale structure we observe today. The prediction is that the universe should be homogeneous, meaning statistically the same in every direction, on scales larger than approximately 1.2 billion light years. Above this scale, the density of matter should be essentially uniform. Structures, coherent arrangements of matter that are denser than their surroundings should not exist on scales larger than 1.2 billion light years. The Hercules-Corona Borealis Great Wall, if confirmed, is 8 to 9 times larger than this theoretical maximum. It is not slightly outside the predicted range. It is not a marginal anomaly that could be accommodated by adjusting a few parameters. It is a structure so dramatically larger than the maximum predicted by the standard model that, if real, it suggests something is fundamentally wrong with our understanding of the universe at its largest scales. The Hercules-Corona Borealis Great Wall, if confirmed, is 8 to 9 times larger than this theoretical maximum. It is not slightly outside the predicted range. It is not a marginal anomaly that could be accommodated by adjusting a few parameters. It is a structure so dramatically larger than the maximum predicted by the standard model that, if real, it suggests something is fundamentally wrong with our understanding of the universe at its largest scales. Let me tell you how this structure was found and what the specific evidence for it looks like, because the method of detection is unusual, and understanding it is important for assessing the reality of the structure. Galaxy surveys, like the Sloan Digital Sky Survey, map the positions of individual galaxies in 3 dimensions by measuring their spectra and determining their redshifts. The redshift tells you how fast a galaxy is receding from us, and combined with the Hubble law, gives you a distance. By mapping millions of galaxies this way, surveys construct a 3-dimensional map of the universe out to distances of several billion light years. The problem with using this method to detect structure at distances of 6 to 10 billion light years, which is where the Hercules-Corona Borealis Great Wall is located, is that at those distances, galaxies become very faint and very numerous. Current spectroscopic surveys cannot obtain spectra for individual galaxies at these extreme distances in reasonable observing time. And photometric surveys, which measure colors rather than full spectra, do not give precise enough distance estimates to reliably identify structures in 3 dimensions. Gamma ray bursts offer a workaround. They are extraordinarily bright, visible from across the observable universe. They can be detected and their redshifts measured spectroscopically even at distances of 10 billion light years or more. By mapping the positions of gamma-ray bursts across the sky and measuring their redshifts, you can construct a sparse but three-dimensional map of the universe at these extreme distances. Istvan Horvath and his collaborators used a catalog of gamma-ray bursts with known redshifts, primarily from the SWIFT satellite, to look for clustering in the distribution of bursts. They found a region of the sky in the direction of Hercules and Corona Borealis where bursts were significantly more numerous than expected from a random distribution. The overdensity was present in a specific range of redshifts corresponding to distances of roughly 6 to 10 billion light years. The angular extent of the overdensity, combined with the depth range in redshift, implied a structure with physical dimensions of approximately 10 billion light years in its longest direction. The statistical significance of the clustering in the original 2014 paper was assessed at a level suggesting the probability of the structure arising by chance was very small, on the order of 1 in hundreds of thousands. Subsequent papers by the same group, using larger catalogs of gamma-ray bursts, found similar results. The structure appears to have persisted across multiple analyses, using data from different time periods. But the skeptical response to these claims has been vigorous and I think legitimate. The number of gamma-ray bursts with measured redshifts in the relevant region of sky is relatively small, a few hundred at most. Statistical claims about structure based on small samples are notoriously sensitive to the specific assumptions made in the analysis, particularly about what the expected random background distribution should look like. Different researchers using different methods of estimating the background have found different levels of statistical significance for the same data. Some analyses find the structure to be highly significant. Others find it to be marginal or statistically consistent with random fluctuations. The honest scientific assessment is that the Hercules-Corona Borealis Great Wall is a genuine candidate for an anomalously large structure that deserves further investigation, but that the current evidence is not strong enough to make a definitive claim. It is a structure that might be real, and that, if real, would have profound implications. It is not yet a confirmed discovery. And the James Webb Space Telescope has been making this problem worse, much worse. Let me start from the beginning, because I think the full story of what we know and what we do not know about the large-scale structure of the universe is more interesting and more important than the headline suggests. And I think understanding the specific way in which the standard model is being challenged, rather than just knowing that it is being challenged, is essential for appreciating what is actually at stake. The standard cosmological model, Lambda-CDM, is built on a foundation of remarkable simplicity. The universe began about 13.8 billion years ago in a hot, dense state. In the first tiny fractions of a second, it underwent a period of extraordinarily rapid expansion called inflation, during which quantum fluctuations in the energy density of the universe were stretched to macroscopic scales. These stretched fluctuations became tiny overdensities, regions where the density of matter was very slightly above average, and underdensities, regions where it was very slightly below average. The amplitude of these fluctuations, how big the overdensities and underdensities were, and the statistical properties of their distribution are specified by the physics of inflation. As the universe expanded and cooled over the following billions of years, gravity amplified these tiny initial fluctuations. Regions that were slightly overdense pulled in surrounding matter, becoming denser. Regions that were underdense lost matter to their overdense neighbors, becoming emptier. Over time, the universe developed the complex filamentary structure we call the cosmic web, with galaxies and galaxy clusters concentrated along filaments and sheets separated by vast underdense voids. The specific statistical properties of this cosmic web, how the density fluctuations are distributed across different scales, how strongly different regions are correlated with each other, what the characteristic sizes of the structures are. All of these are predicted by Lambda-CDM with considerable precision. And for most of the scales we can observe, from individual galaxy clusters up to a few 100 million light years, the predictions match the observations well. The standard cosmological model, Lambda-CDM, is built on a foundation of remarkable simplicity. The universe began about 13.8 billion years ago in a hot, dense state. In the first tiny fractions of a second, it underwent a period of extraordinarily rapid expansion called inflation, during which quantum fluctuations in the energy density of the universe were stretched to macroscopic scales. These stretched fluctuations became tiny overdensities, regions where the density of matter was very slightly above average, and underdensities, regions where it was very slightly below average. The amplitude of these fluctuations, how big the overdensities and underdensities were, and the statistical properties of their distribution are specified by the physics of inflation. Let me be more specific about what inflation predicts, because the specificity is important for understanding why the anomalies are anomalies. The simplest models of inflation, driven by a single scalar field called the inflaton, rolling slowly down a smooth potential energy landscape, predict an almost scale-invariant power spectrum of initial density fluctuations. Scale-invariant means that the amplitude of the fluctuations is approximately the same on all length scales, from tiny scales much smaller than any observable structure to the largest scales accessible to observation. The power spectrum is usually parameterized by a spectral index ns, which for perfect scale invariance would be exactly 1. Observations of the cosmic microwave background give ns approximately 0.965, very close to but slightly less than 1. This small deviation from scale invariance is a prediction of the simplest inflationary models and has been confirmed with remarkable precision. The near-scale invariance of the initial power spectrum has a specific implication for large-scale structure. If the initial fluctuations are approximately the same amplitude on all scales, and if structure grows by gravitational amplification of these initial fluctuations, then there should be no preferred scale in the universe. No scale should be dramatically more structured than any other. The density fluctuations should be statistically random, with the correlation between distant points decreasing smoothly as the distance increases, eventually becoming negligible on scales larger than the correlation length of the initial fluctuations. The scale of homogeneity, roughly 1.2 billion light years, is not a sharp boundary, but a characteristic scale above which the correlations between different regions become very small. Above this scale, the universe should look statistically the same in every direction. The matter distribution should be effectively random, with no preferred axes, no preferred structures, no coherent arrangements extending over billions of light years. This is the prediction. The universe above 1.2 billion light years should be, in the technical statistical sense, homogeneous and isotropic. The cosmological principle, the assumption that underlies all of cosmology, is that the universe is homogeneous and isotropic on the largest scales. Lambda-CDM is the specific model that implements this principle and predicts the specific scale above which it should hold. As the universe expanded and cooled over the following billions of years, gravity amplified these tiny initial fluctuations. Regions that were slightly overdense pulled in surrounding matter, becoming denser. Regions that were underdense lost matter to their overdense neighbors, becoming emptier. Over time, the universe developed the complex filamentary structure we call the cosmic web, with galaxies and galaxy clusters concentrated along filaments and sheets separated by vast underdense voids. The specific statistical properties of this cosmic web, how the density fluctuations are distributed across different scales, how strongly different regions are correlated with each other, what the characteristic sizes of the structures are, All of these are predicted by Lambda-CDM with considerable precision. And for most of the scales we can observe, from individual galaxy clusters up to a few 100 million light years, the predictions match the observations well. The scale of homogeneity is the scale above which the universe should look statistically the same in every direction, where the density fluctuations should be small and uncorrelated. Lambda-CDM predicts this scale to be approximately 1.2 billion light years. This prediction is based on the same inflationary initial conditions that correctly predict the power spectrum of the cosmic microwave background, the pattern of temperature fluctuations in the oldest light in the universe. The prediction is not arbitrary. It is derived from the physics of inflation and from the observed properties of the early universe. The prediction is also not just a number. It is a statement about the fundamental structure of reality at the largest scales. It says that above 1.2 billion light years, there should be no coherent structures, no preferred directions, no coordinated arrangements of matter stretching across billions of light years. The universe above that scale should be featureless, statistically speaking, like a smooth sea when viewed from a great enough height. This prediction has been tested by galaxy surveys for decades. The Sloan Digital Sky Survey, the largest survey of its kind for many years, mapped the three-dimensional distribution of hundreds of thousands of galaxies and found a universe largely consistent with Lambda-CDM at the scales it could access. Structures like the Sloan Great Wall, discovered in 2003 and extending roughly 1.4 billion light years, sat right at the edge of the predicted scale, potentially explainable as a statistical fluctuation. But in recent years, something has been changing. The surveys have gotten deeper, covering larger volumes of the universe, reaching back to earlier cosmic times. And the structures they have been finding have gotten larger than the Sloan Great Wall, larger than the predicted scale of homogeneity, larger than anything the Standard Model says should exist. The giant arc, discovered in 2021 by astronomer Alexia Lopez and her collaborators using data from the Sloan Digital Sky Survey, is a crescent-shaped arrangement of galaxies, galaxy clusters, and gas clouds extending approximately 3.3 billion light years. That is roughly 3 times the predicted scale of homogeneity. The probability of a structure of this size and coherence arising by chance within the Lambda-CDM framework is approximately 1 in 50,000. 1 in 50,000 is not impossible. In a universe as large as ours, rare statistical fluctuations do occur. But 1 in 50,000, combined with the fact that it is not the only anomalously large structure that has been found, starts to suggest a pattern rather than a coincidence. Then there is the South Pole Wall, identified in 2020, extending roughly 1.4 billion light years and containing hundreds of thousands of galaxies. And the Boötes supervoid, a vast underdensity roughly 330 million light years in diameter, which is the largest known void in the universe and represents its own challenge to the predictions of Lambda-CDM. And the cold spot in the cosmic microwave background, a region of anomalously low temperature that some researchers have connected to an unusually large void along the line of sight, and the Claus-Camposano Large Quasar Group, a clustering of quasars extending approximately 2 billion light years that predates the Sloan Great Wall discoveries. Each of these structures, considered in isolation, could be a statistical fluctuation. The universe is large, and rare events do occur somewhere in it. But the accumulation of anomalously large structures, each one exceeding the predicted scale of homogeneity by factors of 2, 3, or more, is becoming difficult to dismiss as coincidence. The pattern suggests that the universe may be less homogeneous at large scales than Lambda-CDM predicts. And then there is the Hercules-Corona Borealis Great Wall. This structure was first identified in 2014 by researchers led by Istvan Horvath, analyzing the distribution of gamma ray bursts in the sky. Gamma ray bursts The extraordinarily energetic explosions I described in the video about neutron-star mergers occur throughout the universe at all distances. Because they are extremely bright, they can be detected at enormous distances, far beyond the reach of ordinary galaxy surveys. By mapping the three-dimensional distribution of gamma-ray bursts, Horvath and his team identified a clustering of bursts in the direction of the constellations Hercules and Corona Borealis at a distance of approximately 6 to 10 billion light-years. The clustering, if real, represents a structure approximately 10 billion light-years in its longest dimension, at its widest roughly 7.2 billion light-years. This is not just larger than the scale of homogeneity, it is larger than any structure that could have formed in the current universe through the gravitational amplification of initial density fluctuations, because the universe is only 13.8 billion years old, and structures can only grow as fast as the speed of light allows causal connections to be established. A structure 10 billion light years in size would have required causal connections across distances that light could barely have traversed in the age of the universe. The structure should not be able to exist coherently, not just because it exceeds the predicted scale of homogeneity, but because it exceeds the causal horizon within which gravitational structure formation can operate. Now, I want to be honest about the uncertainties in the Hercules-Corona Borealis Great Wall, because honesty about the state of the evidence is essential here. The structure was identified using gamma-ray bursts rather than galaxies, and gamma-ray burst surveys have important limitations. The number of bursts in the relevant region of the sky is relatively small, meaning the statistical significance of the clustering depends critically on how the background expectation is calculated. Different methods of calculating the background give different assessments of the significance. Some analyses find the structure to be statistically significant at the level that would ordinarily be called a discovery. Others find the significance to be marginal or dependent on the specific assumptions made in the analysis. The scientific community has not reached consensus on whether the Hercules-Corona Borealis Great Wall is real. Several teams have analyzed the same data and arrived at different conclusions. The challenge is that without a complete and unbiased sample of gamma-ray bursts across the relevant region of sky, it is difficult to distinguish between a genuine large-scale overdensity and a statistical fluctuation. Follow-up surveys using galaxies rather than gamma-ray bursts in the relevant region have been limited by the extreme distances involved, which make spectroscopic galaxy surveys technically challenging. What I can say is this: the Hercules-Corona Borealis Great Wall is a genuine scientific controversy, not a settled matter. It might be real. It might be a statistical artifact. If it is real, it presents a profound challenge to the standard model of cosmology. If it is an artifact, it is still part of a broader pattern of anomalously large structures that the standard model is having trouble accommodating. And this is where the James Webb Space Telescope comes in, because the Webb telescope has been providing independent evidence that something is wrong with the standard model at large scales, and its evidence is more difficult to dismiss than the Hercules-Corona Borealis Great Wall. The James Webb Space Telescope, launched in December 2021 and reaching full science operations in 2022, is the most powerful space telescope ever built. It observes primarily in infrared light, which allows it to see through dust clouds and to detect the highly redshifted light from the most distant galaxies in the universe, galaxies that were forming when the universe was only a few 100 million years old. Webb has the sensitivity to characterize these early galaxies in detail, measuring their masses, their star formation rates, their chemical compositions, in ways that were simply impossible with previous instruments. And what it has found in the earliest galaxies has been deeply surprising. The standard model of galaxy formation, which is an application of Lambda-CDM to the specific problem of how galaxies form and grow within the cosmic web, predicts that galaxies should form hierarchically. Small galaxies form first, by the gravitational collapse of overdense regions in the early universe. Larger galaxies form later by the merging of smaller ones. The most massive galaxies, elliptical giants containing trillions of stars, should be rare in the early universe and more common in the late universe. This hierarchical picture has been supported by observations of galaxies at moderate distances and has been refined into detailed simulations that reproduce many observed properties of the galaxy population. But Webb is finding massive galaxies in the early universe that should not be there. In the first year of science operations, Webb detected multiple galaxies at redshifts greater than 10, corresponding to times when the universe was less than 500 million years old, that are more massive than the Standard Model predicts should be possible. Some of these galaxies contain as many stars as the Milky Way, but in a universe that is a tiny fraction of its current age. They are too big, too organized, too mature for their cosmic age. The discrepancy is not small. The most extreme examples have stellar masses that exceed the predictions of the Standard Model by factors of 10 to 100. They should not exist according to the simulations that have successfully reproduced galaxy populations at lower redshifts. And they are not rare exceptions. They appear in multiple fields, at multiple redshifts, observed by multiple research teams using different analysis methods. The standard response within the cosmological community has been that the mass estimates might be wrong, that photometric measurements of galaxy masses at these redshifts are uncertain, that the galaxies might be less massive than they appear when better spectroscopic data is obtained. This is a legitimate concern. Measuring the mass of a galaxy at redshift 10 from photometric data alone is genuinely difficult, and systematic errors are possible. Some early Webb detections that initially seemed like very massive early galaxies have been revised downward after spectroscopic follow-up. The James Webb Space Telescope, launched in December 2021 and reaching full science operations in 2022, is the most powerful space telescope ever built. It observes primarily in infrared light, which allows it to see through dust clouds and to detect the highly redshifted light from the most distant galaxies in the universe, galaxies that were forming when the universe was only a few hundred million years old. Webb has the sensitivity to characterize these early galaxies in detail, measuring their masses, their star formation rates, their chemical compositions in ways that were simply impossible with previous instruments. The context for understanding what Webb has found requires a brief description of how galaxy formation is supposed to work in Lambda-CDM. The formation of galaxies is governed by the formation of dark matter halos, the gravitationally bound concentrations of dark matter within which ordinary matter collects and cools to form stars. Small dark matter halos form first in the overdense regions of the early universe. Larger halos form later, either by the further accretion of matter or by the merging of smaller halos. The characteristic mass of halos that can form by any given time is set by the amplitude of the initial density fluctuations on the relevant scale and by the time available for gravitational growth. In the very early universe, only small halos could have formed because the density fluctuations on large scales had not yet been amplified enough by gravity to collapse. Large halos and the large galaxies that form within them are expected to be rare at early times. This is the hierarchical picture. Structure builds from small to large. The most massive objects form last. Quantitative predictions from this picture, implemented in detailed numerical simulations called n-body simulations, give specific predictions for how many galaxies of each mass should exist at each cosmic epoch. These predictions have been tested against observations of galaxies at moderate redshifts, out to redshifts of a few, and have been found to agree reasonably well with some tensions that have motivated modifications to the model. Webb is observing galaxies at redshifts of 8 to 16, corresponding to times when the universe was between 300 million and 600 million years old. These are the first galaxies that ever existed, and some of them are too big. Specific examples give a sense of the problem. A galaxy designated JADES GSZ130, observed at a redshift of about 13.2, corresponding to a time 320 million years after the Big Bang, has been found to contain approximately 1 billion solar masses of stars. In the Standard Model, a galaxy this massive at this epoch would require that essentially all the dark matter in a very large halo had been converted to stars with perfect efficiency, with no gas loss to stellar winds or supernovae. The simulations say this is extremely unlikely. A galaxy containing 1 billion solar masses of stars at redshift 13 is expected to occur perhaps once in the entire observable universe, if at all. Webb has found multiple such objects. More recently, a galaxy designated JADESGSZ140 has been found at a redshift of 14.32, making it one of the most distant galaxies ever confirmed spectroscopically. It has a luminosity and inferred stellar mass that challenge the standard formation models even more severely. Its discovery implies that substantial galaxies were already forming within the first few 100 million years of the universe's existence, faster than the standard hierarchical model predicts. Beyond individual extreme cases, statistical analyses of the galaxy population found by Webb at high redshift have found a systematic excess of massive galaxies relative to the predictions of Lambda-CDM. The excess is not a factor of 2 or 3, which might be accommodated by adjustments within the model. It is a factor of 10 to 100 for the most extreme cases, and a systematic factor of several for the population as a whole. This is a genuine discrepancy between the observations and the model, not a measurement uncertainty. The standard response within the cosmological community has been that the mass estimates might be wrong, that photometric measurements of galaxy masses at these redshifts are uncertain, that the galaxies might be less massive than they appear when better spectroscopic data is obtained. This is a legitimate concern. Measuring the mass of a galaxy at redshift 10 from photometric data alone is genuinely difficult, and systematic errors are possible. Some early Webb detections that initially seemed like very massive early galaxies have been revised downward after spectroscopic follow-up, but the revisions have not made the problem go away. The discrepancy has been reduced compared to the most extreme early estimates, but it has not been eliminated. A population of galaxies that are roughly 10 times more massive than the standard model predicts, scattered throughout the early universe at redshifts of 8 to 12, is now a well-established observational fact that requires an explanation. What could explain these massive early galaxies? There are several possibilities, each of which has different implications for the standard model. The first possibility is that star formation in the early universe was more efficient than the standard model assumes. The standard model predicts that only a fraction of the gas in a galaxy is converted to stars because stellar feedback, the radiation and winds from massive stars, and the explosions of supernovae heats the remaining gas and prevents it from collapsing further. If stellar feedback was less effective in the early universe, if the conditions were such that a larger fraction of gas was converted to stars before feedback could suppress it, then galaxies could have been more massive at early times than current simulations predict. This would be an adjustment within the framework of Lambda-CDM rather than a challenge to the underlying cosmological model. The second possibility is that dark matter behaves differently in the early universe than the standard model assumes. The standard model treats dark matter as cold and collisionless, meaning that dark matter particles move slowly compared to the speed of light and do not interact with each other except through gravity. But if dark matter has some self-interaction, if dark matter particles can scatter off each other or decay into lighter particles, the formation of dark matter halos in the early universe would be different. Some models of self-interacting dark matter predict denser dark matter halos in the early universe, which would accelerate the formation of massive galaxies. The third possibility is that the initial conditions of the universe were different from what the standard model assumes. Lambda-CDM is built on specific predictions from inflation about the statistical properties of the initial density fluctuations. If inflation produced a different spectrum of fluctuations with more power on small scales than the standard spectrum, the formation of massive structures in the early universe would be accelerated. This would be a modification to the inflationary model, not to Lambda-CDM itself, but it would change the predictions of the framework in ways that might accommodate the Webb observations. The fourth possibility, the most radical one, is that there is something fundamentally wrong with the standard model at early times and large scales. That the cosmological model we use to describe the universe is incomplete in ways that become apparent when we probe the early universe at Webb sensitivity. This possibility is not necessarily a revolution in physics. It might be a modest extension of the standard model, the addition of new ingredients, or the modification of existing ones. But it would require acknowledging that our current best description of the universe is missing something important. I do not know which of these possibilities is correct. Nobody does yet. The Webb observations are less than 3 years old, and the community is still in the process of analyzing the data, proposing models, and testing those models against additional observations. What I can say is that the observations are real, that they are inconsistent with the most natural interpretation of the standard model, and that the community is taking them seriously as a potential indication that the model needs to be extended. Now let me connect the Webb observations to the large-scale structure anomalies like the Hercules-Corona Borealis Great Wall, because I think the connection is important and illuminating. The standard model is being challenged on two fronts simultaneously. On the small-scale front, at the level of individual galaxies, Webb is finding massive galaxies in the early universe that should not exist according to the hierarchical formation picture. On the large-scale front, surveys like the Sloan Digital Sky Survey and the sources that identified the Great Wall are finding coherent structures much larger than the scale of homogeneity that inflation predicts. Now let me connect the Webb observations to the large-scale structure anomalies like the Hercules-Corona Borealis Great Wall, because I think the connection is important and illuminating. The standard model is being challenged on two fronts simultaneously. On the small-scale front, at the level of individual galaxies, Webb is finding massive galaxies in the early universe that should not exist according to the hierarchical formation picture. On the large-scale front, surveys like the Sloan Digital Sky Survey and the sources that identified the Great Wall are finding coherent structures much larger than the scale of homogeneity that inflation predicts. I want to emphasize a specific aspect of the connection that is rarely discussed in popular accounts. The hierarchical structure formation picture and the scale of homogeneity prediction both derive from the same underlying assumption, that the initial density fluctuations produced by inflation have the specific statistical properties predicted by the simplest inflationary models. If those initial conditions were different from what we assume, if inflation produced more power on certain scales, or if the initial fluctuations were correlated in ways that the standard spectrum does not capture, then both the rate of galaxy formation and the characteristic scale of large-scale structure would be different. In other words, the two sets of anomalies might be two manifestations of the same underlying departure from the standard initial conditions. The massive early galaxies might be telling us that there is more power in the initial fluctuations on the scales relevant to individual galaxy formation. The anomalously large structures might be telling us that there is more power in the initial fluctuations on the scales relevant to large-scale structure. If both anomalies reflect the same modification to the initial power spectrum, then finding the modification that explains one might automatically explain the other. This is a speculative but scientifically motivated connection. Researchers have begun to explore modified inflationary models that could explain the Webb observations and simultaneously reduce the discrepancy at large scales. These models are not yet well developed and have not yet been shown to be consistent with all the other constraints on inflation. But the direction of the research is promising, and the possibility that the two sets of anomalies have a common explanation is worth taking seriously. There is another connection that I want to draw, which is between the large-scale structure anomalies and the Hubble tension. The Hubble tension, which I discussed extensively in the first video in this series and revisited in the video about James Webb and Lambda-CDM, is the discrepancy between the two independent measurements of the expansion rate of the universe. The early universe measurement gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The late universe measurement gives approximately 73. The two disagree by about 8%, well outside the measurement uncertainties. The Hubble tension has resisted resolution within the standard model. Numerous modifications have been proposed, including early dark energy that was stronger in the first 100,000 years of cosmic history, additional relativistic species beyond the known neutrinos, modified recombination physics, and many others. None of these proposals has been definitively confirmed, and several have been constrained or disfavored by subsequent observations. What is interesting about the Hubble tension in the context of the large-scale structure anomalies is that it also points toward the early universe. The two measurements disagree about the expansion rate, and the most natural modification of the standard model that could resolve the tension involves changing the physics in the early universe before recombination in ways that affect the acoustic horizon, the characteristic scale imprinted in the large-scale distribution of galaxies. If the physics in the early universe was different from what the standard model assumes, both the Hubble tension and the large-scale structure anomalies might be affected. This suggests the possibility that all the anomalies, the massive early galaxies, the anomalously large structures, the Hubble tension, are connected, that they are all manifestations of a departure from the standard model's description of the early universe. If this is correct, then the resolution of any one of them might illuminate the others, and the specific form of the departure might be constrained by all of them simultaneously. These might be independent problems with independent solutions. The massive early galaxies might be explained by modified star formation efficiency, while the large-scale structures are explained by some other mechanism. But I find it at least worth noting that both anomalies point in the same direction. Both suggest that the universe is more structured, more organized, more complex at early times and large scales than the standard model predicts. The hierarchical picture of structure formation, in which structures grow from small to large over cosmic time, seems to be violated in both directions. In the large scales where structures should not exist, and in the early times where massive structures should not yet have formed. This pattern, both anomalies pointing in the same direction, is the kind of thing that makes physicists think that something systematic might be wrong with the underlying model, rather than that independent errors have occurred in multiple different measurements. When the data is systematically wrong in the same direction, when every anomaly seems to tell the same story about the universe being more structured than the model predicts, that is a signal worth paying attention to. Let me now take you through what specific modifications to the standard model have been proposed, because I think the proposals are themselves illuminating about what the physics of the situation looks like. The most widely discussed modification is to the nature of dark energy. Lambda-CDM treats dark energy as a cosmological constant, a fixed energy density of empty space that does not change over time. The observed acceleration of the cosmic expansion, which dark energy is invoked to explain, is consistent with a cosmological constant at the current level of, but the cosmological constant is theoretically problematic for reasons I discussed in the video about the cosmological constant problem, and there is no fundamental physical reason why dark energy must be constant rather than dynamic. If dark energy is a dynamical field, if its energy density changes over cosmic time, the expansion history of the universe would be different from the Lambda-CDM prediction. A dark energy that was stronger in the early universe and has weakened over time would have suppressed structure formation at early times and allowed it to proceed more freely at late times. A dark energy that has been strengthening over time would have the opposite effect. Depending on the specific form of the dark energy evolution, it might be possible to reconcile the Webb observations with a modified cosmological model. The DESI survey, the dark energy spectroscopic instrument that I mentioned in the video about James Webb and Lambda-CDM, has provided the first hints from its 2024 data release that dark energy may not be constant. The statistical significance is not yet at the level that would be called a discovery, but the data prefer a dark energy equation of state that has evolved over cosmic time. If this preference is confirmed by future data, it would be the first direct evidence that the cosmological constant description of dark energy is incomplete. And it would open the door to modified dark energy models that might explain the large-scale structure anomalies and the massive early galaxies. The other major modification that has been proposed is to the initial conditions of the universe. Inflation, in its simplest forms, predicts a nearly scale-invariant spectrum of initial density fluctuations, meaning that the amplitude of the fluctuations is approximately the same on all scales. But if inflation was not exactly as the simplest models predict, if it had features that introduced preferred scales or amplified certain modes more than others, the statistical properties of the large-scale structure would be different. Specifically, if inflation produced more power on large scales than the simplest models predict, the amplitude of large-scale density fluctuations would be larger, making large coherent structures more likely to form. This kind of non-standard inflationary initial conditions is not ad hoc. There are well-motivated inflationary models that produce specific deviations from the scale-invariant spectrum. Features in the inflaton potential, resonances or transitions in the inflaton field during inflation, can produce oscillatory or step-like features in the power spectrum of initial fluctuations. These features would leave specific imprints on the large-scale distribution of matter and galaxies, imprints that might correspond to the anomalously large structures that have been observed. Testing this idea requires very precise measurements of the large-scale distribution of matter and of the cosmic microwave background, measurements that the current generation of surveys is beginning to provide and that the next generation will provide with much greater precision. The Simons Observatory, the CMB, S4 experiment, the Rubin Observatory Legacy Survey of Space and Time, and the Euclid satellite are all designed to measure the statistical properties of the large-scale structure with the precision needed to test these models. Testing this idea requires very precise measurements of the large-scale distribution of matter and of the cosmic microwave background, measurements that the current generation of surveys is beginning to provide and that the next generation will provide with much greater precision. The Simons Observatory, the CMB, S4 experiment, the Rubin Observatory Legacy Survey of Space and Time, and the Euclid satellite are all designed to measure the statistical properties of the large-scale structure with the precision needed to test these models. Let me describe what each of these will do and why they matter for the questions I have been discussing. The Simons Observatory, currently being built in the Atacama Desert in Chile, will measure the cosmic microwave background with 10 times the sensitivity of the Planck satellite at small angular scales. Its most important contribution will be measuring the lensing of the CMB by intervening matter, which provides a direct measurement of the large-scale matter distribution at intermediate redshifts. If the matter distribution is less clumped than Lambda-CDM predicts, the Simons Observatory will detect it. The Rubin Observatory, currently being commissioned, will conduct a legacy survey of space and time, mapping billions of galaxies across a large fraction of the sky using repeated photometric observations. Over its 10-year survey, it will construct the most detailed three-dimensional map of the universe ever made, reaching out to redshifts of several, and providing statistics on the large-scale distribution of matter that will either confirm or challenge the predictions of Lambda-CDM with unprecedented precision. The Euclid satellite, launched in 2023, is designed specifically to measure the large-scale structure of the universe and to characterize dark energy. It will observe hundreds of millions of galaxies with spectroscopic precision out to redshift 2, providing the most complete measurement of baryon acoustic oscillations, the standard ruler for cosmological distance measurements that has ever been made. Its measurements will either confirm the standard dark energy model or constrain modifications to it with high precision. Together, these instruments will provide a definitive test of the standard model at large scales over the next decade. If the anomalies I have described are real, if the universe is genuinely less homogeneous at large scales than Lambda-CDM predicts, if the large-scale structure is genuinely more coherent than inflation predicts, these instruments will detect it. And if the standard model is correct, the anomalies will dissolve into statistical noise as the surveys get larger and more precise. I find this to be one of the most exciting aspects of contemporary cosmology. The question of whether the large-scale structure of the universe matches the predictions of Lambda-CDM is not going to remain uncertain for long. The data is coming. The instruments are being built or are already operating. The resolution is probably a decade away. But the most important constraint on any proposed modification to the standard model is internal consistency. Any model that explains the large-scale structure anomalies must also be consistent with the extremely well-measured properties of the cosmic microwave background, with the abundance of light elements produced in Big Bang nucleosynthesis, with the observed clustering of galaxies at smaller scales, and with the distance measurements from type Ia supernovae that establish the acceleration of the cosmic expansion. The standard model is not just a collection of assumptions. It is a highly constrained framework that has been tested against dozens of independent observations. Any modification that explains one anomaly while breaking the agreement with other observations is not an improvement. This is why finding the right modification to the standard model, if one is needed, is such a difficult problem. The model is well tested, its successes are real and extensive. The modifications that would help with the large-scale structure anomalies must be small enough to preserve the model's existing successes while large enough to resolve the anomalies. Finding that sweet spot is a challenging theoretical and observational problem. I want to say something honest about the state of the field right now, because I think it is important to convey accurately. The anomalies I have described are real. The Hercules-Corona Borealis Great Wall is a genuine candidate for an anomalously large structure. The giant arc is a well-documented anomaly, with a probability of about 1 in 50,000 within the standard model. The massive early galaxies found by Webb are confirmed observations that the standard model does not easily explain. The Hubble tension, which I discussed in the first video in this series, has not been resolved and continues to deepen, but the standard model has not been falsified. It has not been shown to be definitively wrong. Each individual anomaly has a natural explanation available within the standard model, if one is willing to invoke sufficiently rare statistical fluctuations or unmodeled systematic errors. The scientific community is not in a state of crisis, in the sense of having abandoned the standard model or agreed that it needs to be replaced. There is active debate, active research, active proposal of modifications and extensions. But there is not yet a clear consensus about what the anomalies mean or what the right response to them is. What I think is honest to say is this: the accumulation of anomalies, each one individually explainable but collectively suggesting a systematic pattern, has reached the point where the most intellectually honest response is to take seriously the possibility that the standard model is missing something at large scales and early times, not to abandon the model, which would be premature, not to dismiss the anomalies, which would be intellectually dishonest given their persistence and coherence, but to engage seriously with the possibility that the universe at its largest scales is telling us something that the model we built does not yet capture. There is a historical pattern here that I think is worth noting. The history of physics is full of moments when anomalies accumulated against a successful model, when the anomalies were individually explainable but collectively suggestive of something deeper, when the scientific community gradually shifted from explaining the anomalies away to taking them seriously as signals of a needed revision. The perihelion precession of Mercury accumulated as an anomaly against Newtonian mechanics for 40 years before general relativity explained it. The ultraviolet catastrophe, the failure of classical physics to correctly predict the spectrum of blackbody radiation, was known for years before Planck proposed the quantum of action. The rotation curves of galaxies showed excess velocity at large radii for decades before dark matter became the accepted explanation. Each of these transitions involved a period of anomaly accumulation, a period in which the standard explanation was insufficient, but no better explanation had been found. A period of genuine scientific uncertainty before the resolution arrived. I think we are in such a period now with respect to the large-scale structure of the universe. The James Webb Space Telescope has accelerated this period by providing unprecedented data on the early universe. In the first 2 years of science operations, it has found more anomalies than any previous instrument in a comparable time. It has found massive galaxies that should not exist. It has found structures in the early universe that challenge the hierarchical formation model. It has found chemical enrichment and black hole growth at early times that the standard model did not predict. The telescope is doing exactly what it was designed to do, seeing further and earlier than any previous instrument. And what it sees does not fully match what the model predicted. This is not a failure of the telescope, it is a success of science. The point of building instruments like Webb is to test our models against new data. When the data disagrees with the model, that is not a problem, that is progress. That is the signal that the model needs to be refined or extended. That is the universe telling us, through the mediation of a $6 billion telescope, that our description of its large-scale structure at early times is not quite right. I want to close with something that I think is important and that I do not want to get lost in the specific anomalies and proposed modifications. The question of what the universe looks like at its largest scales and earliest times is not just a technical question about cosmological models. It is a question about the nature of reality at the most fundamental level. The standard model of cosmology, Lambda-CDM, is built on specific assumptions about the initial conditions of the universe, about the nature of dark matter and dark energy, about the properties of inflation. These assumptions are not arbitrary. They are motivated by theoretical considerations and confirmed by many observations. But they are assumptions, and the history of physics tells us that assumptions made in the absence of direct observational evidence are sometimes wrong. The most profound discoveries in the history of cosmology have come from observations that contradicted the prevailing assumptions. The discovery that the universe is expanding, that the expansion is accelerating, that the universe was once much hotter and denser, that the structure we see grew from tiny quantum fluctuations in the very early universe. Each of these discoveries required revising assumptions that had previously been considered secure. The anomalies that James Webb is finding and that the large-scale structure surveys have been accumulating might be leading us to the next such revision. A revision in our understanding of how structure forms in the universe. A revision in our understanding of the initial conditions set by inflation. A revision in our understanding of the nature of dark energy. Or possibly a revision more profound than any of these, a revision in the framework itself, in the way we think about the large-scale geometry of the universe and the physics that governs its evolution. The Hercules-Corona Borealis Great Wall, if it is real, is a structure that should not exist in any universe described by our current best model. And that fact, the fact that something in the universe should not exist according to our best model, is not a reason for despair. It is an invitation. It is the universe telling us that our model, good as it is, does not yet capture everything. That there is something at the largest scales, something about the way the universe is structured on the grandest canvas that we have not yet understood. Scientists are running out of explanations. That is true in a specific technical sense. The explanations within the existing framework are becoming strained. The parameters that can be adjusted are being adjusted to their limits. The statistical coincidences that can be invoked are being invoked more and more frequently. The model is being asked to explain things it was not designed to explain. When scientists run out of explanations within a framework, two things can happen. They can conclude that the data is wrong, that the anomalies are artifacts of measurement error or systematic bias or a statistical fluctuation. Or they can conclude that the framework is incomplete, that the anomalies are real signals of physics that the framework does not yet describe. The history of science suggests that when the anomalies are persistent, when they survive better data and more careful analysis, when they come from multiple independent sources and point in the same direction, the second conclusion is more often correct. The anomalies tend to be real, the framework tends to be incomplete. And the incompleteness, when eventually understood, tends to reveal something profound about the nature of reality that the old framework had hidden. We may be in that moment now. The universe, at its largest scales and earliest times, may be showing us something that our current cosmological framework cannot accommodate. Something about the structure of the cosmos that requires new physics or a new framework, or at minimum a significant revision of the model we have built with such care over the past century. The James Webb Telescope is not just finding anomalies. It is drawing the map of the frontier. The frontier where our best model meets the universe and the universe does not quite fit the map. And that frontier, uncomfortable and uncertain as it is the most interesting place in science to be. The James Webb Telescope is not just finding anomalies. It is drawing the map of the frontier where our best model meets the universe, and the universe does not quite fit the map. And that frontier, uncomfortable and uncertain as it is the most interesting place in science to be. The James Webb Telescope is not just finding anomalies. It is drawing the map of the frontier where our best model meets the universe and the universe does not quite fit the map. And that frontier, uncomfortable and uncertain as it is the most interesting place in science to be. Let me say something about the historical significance of what Webb is doing, because I think the context matters. Every major telescope in the history of astronomy has changed what we know about the universe. Galileo's telescope showed that Jupiter has moons and that the moon has mountains, establishing that celestial objects are physical things rather than eternal, unchanging spheres. The reflecting telescopes of Herschel and Rosa revealed the structure of the Milky Way and the existence of other galaxies. The spectroscopes of the 19th century revealed that the sun and stars are made of the same elements as the Earth, connecting the terrestrial and the celestial. The 100-inch Hooker telescope at Mount Wilson allowed Hubble to measure the distances to galaxies and discover the expansion of the universe. The Hubble Space Telescope launched in 1990, transformed our understanding of galaxy evolution, the expansion history, and the large-scale structure of the cosmos. Each of these instruments did not just confirm what was expected. Each one found something unexpected, something that changed the questions being asked, something that shifted the frontier. Galileo did not expect to find mountains on the moon. Hubble did not expect to find that the universe was expanding. The Hubble Space Telescope's discovery of dark energy was not anticipated by the majority of cosmologists. James Webb is the latest in this lineage. It was built to answer specific questions about the formation of the first stars and galaxies, the atmospheres of exoplanets, and the physics of the nearby universe. But the most important discoveries it is making are not the ones its designers expected. The massive early galaxies, the anomalously rapid formation of structure, the chemical enrichment at early times, these are surprises. And surprises in the history of astronomy have been the drivers of the most profound advances. I find this pattern genuinely exciting rather than alarming. The fact that Webb is finding things that challenge the standard model is not a sign that cosmology has failed. It is a sign that cosmology is working. The purpose of science is not to confirm what we already believe. It is to find out what is true. And finding out what is true sometimes requires discovering that what we believed was not quite right. The anomalies that Webb is finding are not anomalies in the sense of errors or noise. They are anomalies in the sense of data that does not fit the expected pattern, data that requires explanation, data that points towards something in the universe that we have not yet understood. That is the most valuable kind of data in science. It is the data that drives progress. Let me close with something that I think goes beyond the specific anomalies and the specific observational programs, something that connects to the deepest conceptual foundations of the science I have been describing. The cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales, is not just a working hypothesis that happens to be convenient. It is the foundational assumption of modern cosmology. Without it, the mathematical framework of cosmology as we practice it would not work. The Friedman-Lemaitre-Robertson-Walker metric, which describes the expanding universe and underlies all our calculations of cosmic distances and ages, assumes that the universe is exactly homogeneous and isotropic. Every measurement we make of the Hubble constant, of the age of the universe, of the distance to distant galaxies, implicitly assumes that the cosmological principle holds. If the cosmological principle fails at scales larger than the scale of homogeneity, if there are coherent structures at scales of billions of light years, then the universe is not as simple as we assumed. The FLRW framework, which has been so successful, may be an approximation that works well at the scales we have tested, but that fails at larger scales. The cosmological principle might be like the flatness of the Earth, a good approximation locally, but wrong at large enough scales. This is not a catastrophic conclusion. Science routinely discovers that approximations which work at small scales fail at larger scales. Newton's mechanics is an approximation to special relativity, which is itself an approximation to general relativity. Each level of approximation works within its domain and fails when the relevant parameters, velocity, curvature, become large enough. The cosmological principle might be the same kind of approximation, valid at the scales of galaxy clusters and superclusters, breaking down at the scales of the Hercules-Corona Borealis Great Wall. But a failure of the cosmological principle at large scales would require revising not just the Lambda-CDM model, but the entire mathematical framework of cosmology. It would require developing new tools for describing and analyzing a universe that is not homogeneous and isotropic at the largest scales. It would require asking new questions about what the large-scale structure of the universe actually looks like, questions that the current framework is not equipped to answer. This is the deepest version of the challenge that the anomalies pose. Not just a modification to a parameter or an addition to the ingredient list of Lambda-CDM, a potential challenge to the foundational assumption that underlies the entire framework. And that is the kind of challenge that historically has preceded the most profound revisions in our understanding of the universe. I do not know whether the cosmological principle fails. The evidence is suggestive but not conclusive. The Hercules-Corona Borealis Great Wall might be a statistical artifact. The massive early galaxies might be explained within the existing framework with modified assumptions about star formation. The Hubble tension might be resolved by a systematic error in one of the measurements. Each of these possibilities is genuine. None has been ruled out. What I can say is that the universe, examined with the most powerful instruments we have ever built, is showing us something that our current best description does not fully accommodate. The map and the territory do not quite match, and the mismatch, wherever it leads, is telling us something important about the cosmos we inhabit. If this changed how you think about the standard model of cosmology, if the accumulation of anomalies feels more significant to you now than it did before, tell me in the comments. Tell me which anomaly you find most compelling and why. Tell me whether you think the Hercules-Corona Borealis Great Wall is real and what it would mean if it is. And subscribe if you want to stay at the frontier where the observations are coming in faster than the theories can keep up, because that is where the next revolution in our understanding of the universe is being born.